Welcome, welcome, welcome. Another edition, Physical Chemistry. Here I am with my Glenlivet, ready to talk kinetics. Here we go. Now we last left talking about sequential reactions where A goes to I goes to P, our product, I, our intermediate. So in the previous one, we looked at our two extremes, that what happens when A is much, much faster than I, and so we have a buildup of I. Well, what happens when I is much, much faster than Ka? So I never really has a chance to build up. So that's where we get the idea of rate determining steps. The two-step reaction, which one is faster? Is the first step faster or the second step faster? And that will play a part in when we look at the overall rate law. These two limits give rise to important approximation. So the idea, one of these is much slower. The slow step will actually control the rate that we observe, regardless of the other step. What generally happens is the rate determining step, the rate constant related to this slow step, will overwhelm and negate whatever the fast step is. So we won't really care about the fast step. We'll look at it in two different situations. So imagine one constant getting infinitely larger than the other. We can do a limit of the product concentration as K sub A approaches infinity. So we say we're looking at, well, I is A sub 0 plus 1 Ka e the negative kt. It's Ki e to the negative Ka kt. Ki Ka. Let's imagine this as Ka approaches infinity. As this approaches infinity, this is just infinity. Ki minus infinity is essentially negative infinity. And Ki e to the negative Ki, that's going to approach 0. So essentially you're going to have K and Ka, negative K, canceling itself out in negative e to negative Kit. So simplify, if Ka is infinitely faster than Ki, then the concentration of P is only dependent on time and our Ki constant and our initial concentration. So i.e. the first step is fast. We almost entirely ignore the rate constant of the first step. Now let's do the same thing if the second step is fast. As Ki approaches infinity, so negative infinity, it's going to approach 0. We have negative infinity right there over positive infinity, so it's negative. You get the opposite, that the concentration P relates to A sub 0, 1 minus K, 1 minus e to the negative Kat. The second step is fast. Concentration P only depends upon the time, the rate constant for it, the first step, and the initial concentration. Now, when is this approximation appropriate? One case is of where a 20-fold difference is reasonable. So if the concentration of K, if the rate of Ka 20 times greater than Ki, you can make this assumption. If it's kind of in the middling, that becomes a little bit harder. But that's kind of what we're looking at. So one more thing we can look at is called the steady state approximation. Another way to approach these sequential reactions is the steady state approximation. The case where the first step is considerably slower than the subsequent step, we make this approximation that's saying that that the intermediate concentration essentially remains constant through the majority of the reaction. It builds up, and then as soon as it builds up, it's consumed, so it stays more or less constant. So it's very useful if there's more than 2 elementary steps. So we're saying essentially, then the intermediate in this reaction, concentration remains low, and the rate of change is approximately 0, so that we can say di dt is 0 for the majority of the reaction. So as I said, dA dt is equal to negative Ka times A. And di dt is equal to Ka of A, negative Ki of I, and dP dt is Ki of I. Well, we were able to say that if a steady state approximation, we set that equal to 0, and set that Ki times I is equal to Ka times A. So the point is that it's possible to solve the concentration of I only in terms of Ka, Ki, and A. 2 constants and the concentration of A. Now, so how are we doing? So we said dA dt is negative Ka. We can solve that. We set that equal to, we know what A is, A naught E negative Ka T. Because of that, we've already found that. We already found that relationship that A equals A naught E negative Ka T. And so, well, can solve for Ki, solve for this, setting those equal, solving that. So saying that I is then Ka over Ki, A naught E negative Ka times T. And thus, if we have I, we essentially get down to brass tacks. We get the change in rate of P is Ka A naught E negative Ka times T. So checking that assumption. Check that assumption. So we're making the assumption that di dt is equal to 0. So if we take the integral of what we said I was, or not the integral, the differential of what we said I was, does that give us 0? So that's a constant that factors out. A naught is a constant that factors out. So we're doing the only thing that relates to t is the negative, was the E negative Ka T. If we do the integral or the differential of that, that's going to be negative Ka E negative Ka T. Factoring that negative Ka out there, so we get the negative Ka squared over Ki, A naught E negative Ka T equals 0, saying that if Ki is much, much greater than Ka squared A naught, that will equal 0. Well, so essentially saying, for this assumption, the rate for a steady state approximation, if Ka is much, much smaller than Ki, the squared divided by a big number, e to the negative Ka, which is going to be a small number, it's going to eventually, should essentially approach 0. Will be close to 0. Meaning, essentially, a steady state approximation shows that if the second step is significantly faster than the first, the second step will have little to no effect on the actual rate. It's just one more way to approximate this. So we want to show that the relative error in the predicted product of the sequential reaction after 10 seconds with and without the steady state. The initial concentration of A equals 0.53 molar, and 0.2, and Ka is 0.2, and Ki is 3.2. We're looking at the steady state of, so this is without the steady state approximation, this is with the steady state approximation. So let's look at this. Now let's do first with the steady state. The initial concentration is 0.53. First, actually, let's compare how much bigger is Ki than Ka. 3.2 divided by 0.2. How much bigger? 3.2 divided by 0.2 is 16 times bigger. 16 times bigger. So not quite 20. So let's see how much error this actually occurs. So steady state approximation 0.53 times 1 minus e to the negative 0.2 times 10. So e to the negative 2. So e to the negative 2 is first is 0.135. So 1 minus 0.135335283. I'm not rounding right now. Times 0.53 concentration. So the steady state approximation says we have 0.45, we'll say 8 molar product after 10 seconds. Now let's look at the same thing without the steady state. A lot messier. So start with 0.53. 1 plus 0.2 e to the negative 3.2 times 10 minus 3.2 e to the negative 0.2 times 10. Already out of room. So all that is over. All over 3.2 minus 0.2. So that's going to be 3 on bottom. That 0.2 times e to the negative 32 is really, really small. Really, I'm going to say that's 2.532 times 10 to the negative 15. Almost too small to count. And we have 3.2 times e to the negative 2 is 0.433. 0.433. So really little. That first one, let's so that is the first one really doesn't count for much. It's more or less a rounding error. But I'll include it in here. I'm not going to round 3.2. Got to make sure I'm not screwing up this. I'm not going to round. I'm going to take both counts. I'm not going to forget this. Not going to not include it. So combining those two terms together, it's still negative 0.433 divided by 3 plus 1, 0.8556 times 0.53, I get 0.453. So let's take 0.453 minus, so what's the actual error? So 0.458 minus 0.453 divided by 0.453, I have a 1.1% error, considering it's only 16 times greater, not 20 times greater. So the error is not really that significant, all said and done. The steady state approximation is rather valid and a lot easier to take care of, because that whole term essentially drops out to being too small in the long run. So now, up until now, we've only talked about reactions that produce one product. What about multiple reactions that occur? This is often the case in organic chemistry. You might have a kinetic product and a thermodynamic product, depending on the rate law. So this is a reaction where A could go to C, A could go to B, and they each have a rate law of A goes to C, which becomes KC, goes to B, KB. This is commonly referred to as a parallel reaction. That reaction can run in sync with each other. Also called side reactions if we're producing a non-preferred product. So the change in C is going to be what? KCA. The change in B is going to be KBA. But the change in A is going to be the rate of the first reaction going to B, and the rate of the second reaction goes to C. Now, because they both depend on the concentration of A, we can separate the KB and KC as one term. Separate KB and KC as one term, with the idea that the overall reaction, A sub 0 is not equal to 0, and B and C start at 0 at time 0. Remember, as we integrate that, we said A equals A naught E to the whatever the constant out is out in front of that. We solve for that. Well, this constant, instead of being Ka, is now Kb and Kc together. So those two terms get put into there so that the concentration of A related to both of those speeds, the sum of both of those speeds based on the integration of that. But for B and C, it's a little bit different story, because when we plug in A, we have this situation. When we integrate this to solve for B, we get neg. So essentially, we're integrating that. Kc staying constant. B equals Kb. Kb over Kb plus Kc naught of this mess. And C is going to be the same thing, except, but like, what? And if C is, if our of our constant C is Kb over Kb plus Kc A naught, we get essentially this format. We can't just not include that C. 1 minus that. The same is held true for C. The only difference is that whether it's Kb or Kc on top of this overall reaction. So it turns out if we divide by B and C, all of the rate constants cancel out to be that the ratio of B to C is equal to the ratio of Kb to Kc. So these two parallel reactions, the ratio of both concentrations have no dependence on time, no dependence on anything other than the ratio of their relative rates. So KB is going to be one rate, and KC is another rate. So depending on how much of each product depends on their relative rates. And of course, as we'll learn later, rate will have to do with activation energy. And activation energy will have to do with, say, rates will have to do with temperature. And so they may fluctuate at different temperatures, which is why you can favor one product over another by favoring different temperatures. And change, because maybe the rate of KB will change with temperature at a slower rate than KC. So you can favor more B or less B. In fact, we can talk about the yield phi with respect to one product as the K over the sum of all the Ks. So out of the hypothetical 100% yield, how much does B make up? So it's possible to do that. So in a competing reaction, A is converted to B and C with a relative rate of 11 to 1. So 11 to 1 of B to C. What would be the expected yield we could get given enough time? So essentially we're at, so essentially 11 to 1 is going to be our KB, KC. Well, our yield would be what? 11 over sum of all the K's, 12. Given enough time, we'd expect to get 91% yield. Because every time we formed one, we're taking the sum of all of them. Every time we formed one of C, you would form 11 B's, and quickly would outpace the other. Okay, yeah, as I'm saying here, we have the rate dependence of K. It's on, like previously mentioned, rate will depend on K. It's on this Arrhenius equation that relates K to T. K is equal to A, which is a frequency factor, exponential of negative activation energy over RT. So the activation energy is of each step. So now we can actually take the natural log of both sides, give us a linear plot, so we can look at how does K depend on the inverse temperature. The ln K depends on inverse temperature, and that would give us our activation energy as over R as a slope, and natural log of our frequency factor as our y-intercept. We'll be doing that a lot. So we look at two steps with different activation energies. We're going to have looking at two Ks that are going to depend greatly on temperature. So now, not all reactions will perfectly follow this behavior. So they might have to be adjusted by a factor of T to the M. Not really going to have to deal with that too much. So this one, a lot of situations. So a rate of 54 seconds at 298. What temperature would need to be cooled to get a rate of 15 per second if the activation energy is 23 kilojoules? So let's say ln of 54, 15 inverse seconds, cancel out. Watch our units, 23 kilojoules, 8.314 joules per mole Kelvin. So what does that mean? That needs to be times by 1,000, 1 over T2, 298. So let's do that. ln of 54, 15 is 1.28. Multiply by our R. Divide by our EA. get a really small number. So I right now have 0.00046303 equals 1 over T2, 1 over 298. So I'm going to add 1 over 298 to both sides. That's going to give us 0.003818,734 is 1 over T. You really want to make sure you don't round this too prematurely and lose a lot. So I invert that to get the temperature needs to be cooled to 261.86, which in terms of Celsius is negative 11.2 degrees Celsius, 11.2. So it needs to be cooled down pretty low in order to decrease the rate constant by that factor. Now we have a few more reactions we have to deal with before we get to the next chapter. That's reversible reactions, where we can establish equilibrium. We're going to do that. All these reactions so far have just been one way. Essentially, the activation energy barrier is too great to go backwards. But some of these guys, the activation energy is going to be not too high to head backwards. So how do we deal with this if this is reversible? So if the energy of the activation energy forward is similar to activation energy of reverse, we can have this reversible situation. So we can have Ka to B's, we can have a Kb, or B goes to A. So the rate of change of A is going to relate to negative Ka times A plus Kb of B, because that's going to be the constant that's going to depend on the formation of A and the consumption of A. Opposite is going to be true for B, negative Kb of B plus Ka of A. So while there is only reactant at time 0, at any time during the reaction, their A0 must equal the sum of A and B. A plus B cannot give us more than we originally started with. But okay, so doing some complicated math here. So we're going to, because we can't exactly differentiate with respect to A. Okay, we can't exactly integrate this as is because we have two variables, A and B. So how are we going to deal with this? Well, because we say that A sub 0 has to be equal to A and B at any given time, we can say that B is equal to A sub 0 minus A. So plugging that in, now we have it in just in terms of A. This is something now we can integrate. So factoring out all the A terms, knowing A sub 0 is constant, we can get that to the other side. Divide both sides by A sub the whole thing to get T by itself. The time, we'll maybe leaving the negative sign. So send that up and then integrating. So 1 over essentially number x minus constant gives us what? Negative T. We have to integral by parts of essentially like ln Ka Kb A minus Kb A0 minus what? Like negative 1 over Ka Kb ln Ka. Oh, A0 minus Kb A0. I think I have a typo here. I think this whole thing should be in parentheses. Yeah, well, this whole thing should be in parentheses. So essentially, here, let me just fix this on the fly. Goodness. Okay, let's see. Yeah, it doesn't show it in here, but it should be. I must have lost that parenthesis somewhere along the way. Oh, for God's sake. Let's fix that on the fly. Assuming my computer doesn't freeze. Boop, boop. There we are. Huzzah. That log. Integrating that by part puts us at there we are. Okay. There we are. That's more elegant. So integrating that from A to A0. Let's see, we have this is kind of a mess, but kind of not, because when we factor that out, when we subtract the two natural logs, you can have them divide by each other. So Ka, Kb, A0 over Ka, Kb, A0. The Kb's cancel out, so you have just Ka, A0 on bottom. Negative t, and you can take the negative to the Ka, Kb to the other side, so you have negative Ka, Kb, t, ln of that. Finally, if you take the exponential of both sides, you can get Ka and A0 on the other side, and add Kb, A0, and divide by Ka, Kb to get just in terms of A. So for this guy, where you have, okay, so the concentration of A, you put A0. Let's look at this. Let's look at this real quick. E negative K. Let's look at this in the note. Okay, how are we doing the math here? So we have, no, I'm just going to say EX. I'm going to leave all that there because otherwise we have a hot mess. A0 plus KB A0. And then we divide both sides by Ka plus KB. So, and then here I just factored the A0 out. Yeah, okay, yeah. So plugging that back in, if that is all equal to concentration A, and B is concentration is equal to A0 minus A, well then A0 minus this hot mess is going to give, if you factor the A0 out, 1 minus all that hot mess. So we have a way to calculate these guys in terms of each other, just in terms of the constants and time. Okay, there we go. I don't know why it wasn't switching. So as long as A exists, it will go to B and vice versa. Because it's at equilibrium, we cannot get unlimited A, or we can't get 100% A or 100% B. But there will be a point where the rate of the forward reaction and the rate of the reverse reaction will equal 0, which is our equilibrium. Beauty of this. So what is the limit of A, or A at equilibrium, if we allow time to go to an infinity? So let's jump back and look at this equation. If this is what's the limit of A, if we let time to go to infinity, well, this all cancels out, so it's negative infinity. This whole term goes to 0, and so you have KB over KA plus KB. So, and that's what you have, A0 KB KA over KB. And similarly, if we allow time to go to infinity, B is equal to 1 minus KB over KA plus KB. So, and so since the rate of change of these guys at equilibrium is 0, we can say that, oh, that negative KA and KBB 0, we can solve for these two to say that our equilibrium constant is the concentration of products of reactants. There's also the rate of the forward reaction over the rate of the reverse. Essentially, in here, we found the basis for equilibrium in terms of kinetics rather than in terms of Gibbs. That equilibrium is dependent equally on Gibbs free energy, but it's also equally dependent on the kinetics of our forward and reverse reaction. The last thing I'll leave you with is, what is our equilibrium constant given the rate of the forward reaction and the rate of the reverse? Well, actually, what is the rate of the reverse if our equilibrium constant is 500? So if our forward reaction is 0.54, and KB, we want to know what is KB. So I'm going to just say 0.54 divided by 500 is equal to KB, which is 0.00108. So I'm just solving for that. So KB is significantly slower than KA. Jumping back a second, looking at this, but if this is significantly slower, you can say that A is going to be A sub 0 over KA. Or, okay.
Am I distracting?
Yes.
Mama needs medicine.
Okay. That's where I'm going to leave you for tonight. Good night.